And then, so after our classes today and Wednesday, we won't have any more instruction. And really, even the instruction today and Wednesday is going to be review. We're not going to learn any new material. We're just going to be learning new applications or practicing new applications of forces and Newton's laws. So today we're going to focus at the beginning a little bit on angled forces, and then go back and talk about friction some more and practice some problems with friction. And then on Wednesday, we're going to combine those two things. What if there's both angles and friction? And we'll practice some problems like that on Wednesday. So really nothing new in terms of content, just new in terms of applications and different styles of problems you could see. You can see the reminders on the screen. I don't need to go over those, I don't think, just that we have our assessment next Tuesday, and it will be the Positive Physics Unit 12 assessment. That'll be your final exam. It's 20% of your overall semester grade, and it'll be 30 questions. You can see on the Positive Physics website how many from each category there will be, and then the review material that I've suggested numerous times. Today we're just going to go through the notes, and then with whatever time there is, the notes or examples, I guess, more accurately. And then with whatever time is left, you can stick around and ask questions, or you can just on your own begin or continue reviewing for the exam. So any questions about schedule or what to think about preparing for the exam before we jump into today's practice? All right, let's go ahead and get into the different kinds of problems you might see then. So I think I might have even teased this question before when we got to the end of one of the lessons last week. But this example is where we're going to start thinking about angled forces. So instead of just vertical and horizontal, force pulled at an angle that we would need to then break down into its components. So for this one, we see a 5-kilogram object, and we have a force of 30 newtons being exerted at a 30-degree angle to the horizontal. And because this box has 5 kilograms of mass, we could figure out what the weight is. And it's resting on a level tabletop. We're going to assume that we can use 10 for our value of g, the acceleration due to gravity. And they're also telling us for this problem, we can ignore friction. So maybe it's like Teflon on Teflon, so it's super low friction and not something we need to worry about. Or maybe it's even got some lubrication that makes it even less friction. Whatever, we can ignore friction in this case. So to solve this kind of a problem, we're going to use all the skills we've already learned, but just applying them in a new way. So how many forces are acting on this orange box? You can just hold up fingers for however many you see. Seeing mostly 3s. Okay, let's break this down. The question we're going to be asked to, actually, first, what is the force exerted on the box by the table, which is the normal force? So there's one. Hopefully you were thinking of that one as one of the ones that you listed or were recognizing. And then the second thing we're going to try to calculate is how much would this box accelerate with this given force? All right, so if we think about the forces at play, we've got the weight force going down, which is represented here by a green vector arrow. We've got the normal force going up, which was already kind of indicated in the first part of the question, showing us one of the things we want to calculate. And then we've got this angled force at 30 newtons at 30 degrees to the horizontal. So that is those are the only forces, just those 3. Since it said we could ignore friction, we don't have a backward force. And even though this angled force can be broken into components, that doesn't mean there's 2 separate forces. There is just one angled force. Mathematically, we can just determine, well, what's the vertical impact of this one angled force, and what's the horizontal impact of this one angled force. So we wouldn't consider it 2 separate forces. It is just one force going at an angle. We just can find its mathematical magnitude or impact using trig. So 3 forces are what we have acting on this 5-kilogram object. All right, so any ideas why they have drawn this green downward weight vector so much larger than the purple upward normal force vector? Andy, I think your hand up there.
Yeah, would it be because gravity is exerting a greater force?
So they're saying gravity's force is larger than normal force. That's the reason. Any idea why that's true? Nat?
Because of the angled pull force?
Okay, can you expand on that a little bit? What about that angled pulled force would make a difference?
Because it's being pulled at an angle, it causes for gravity to have a greater force because the normal force and the pull force are kind of like combined-ish.
Good. So if you remember back a couple weeks ago now, before Thanksgiving, so quite a while ago, we drew free body diagrams for a number of different scenarios. And with those free body diagrams, we practiced writing force balance equations. And so for this one, vertically speaking, the weight force downward is a fixed value. It's just the mass of the object times the acceleration due to gravity. So it is just a certain number. But the normal force is just however much the table has to support. And since someone is pulling at an angle upward, some of their pulling force is reducing how much the table has to support. That weight force downward would equal the normal force plus the vertical part, the vertical impact of that angled pulling force. So if we were thinking about an equation for that, it would be Fg equals Fn plus the y component of the F pull, right? We could come up with an equation like we did a couple of weeks ago. All right, so those are the three forces, and that is why we have a larger vector arrow for the weight force. If we draw it as more of a true free body diagram and just put those forces onto a central dot where the dot represents the box, it looks like this, and we can see again clearly the three forces. We know that the 30 Newton force of pull was given, and we can easily find the weight because weight's always straight down to the center of the earth due to the gravitational force field of the earth, which is because of the mass that the earth possesses. And they are using 10 here, like the instructions said. You could use 9.8 if you are doing this on your own or for the AP exam. You would need to use 9.81 if it was on the Positive Physics website, just to remind you of that. So here they just use 10, 5 kilogram mass times 10 in terms of the acceleration due to gravity. So the weight force would be 50 newtons in the downward direction. They haven't used the negative because on the free body diagram, you can see it's downward. So, I mean, they could have used negative 10 and made it a negative 50 newtons, but they're just, I think, recognizing, well, you can visually see on the diagram that it's downward, so they're not adding the negative to that. All right, so we can calculate that. There's no way to directly calculate the normal force. There's not like a specific equation like normal force always equals this. The normal force is variable depending on all the other forces that are interacting. So there's not a set equation. And then the pulling force was given, so it's already on the equation or on the diagram. So the next thing we need to do is figure out what those two component forces would be. So like Nat said, there is this upward portion of the pulling force, and there would also be this horizontal portion of this pulling force. If we are to use the 30-degree angle, which was given, then the vertical portion of that angled red vector would be using sine, or we could find it using sine, because the sine of 30 would equal the opposite over the hypotenuse. And the opposite would be that vertical component, and the hypotenuse would be the 30. So then if we rewrite it, it would just be 30 times the sine of 30 equals the vertical component. And the sine of 30 is 0.5. So 30 times 0.5 is 15 newtons. So that vertical component is 15 newtons. And to find the normal force, that's all we need. But part B was find the acceleration. And we're going to need the x component to do that. So they went ahead and found it here. If we're using the 30-degree angle, then the x component is adjacent to that. So we have the use of cosine here to find that adjacent side. And it's still going to be 30 times cosine of the angle of 30, which is 0.866. So that horizontal component is 25.98 newtons. Now, on this picture, it looks as if, because they've used arrows, that those two blue vectors are actually forces. And they're not really forces. They are just the components of that single red pulling force. So if the AP exam in May asked you to draw a free body diagram, and it will usually say, don't draw component forces. So you would not draw these blue arrows on there as if they were separate forces. You could draw dotted lines to illustrate that you're going to use triangulation to find the components, but you shouldn't really draw them as arrows like the textbook has done here, in my opinion. because College Board doesn't want that when they ask you to draw it. But I think here they're just trying to show you that we do need to find those components to solve the problem. Questions about the steps we've taken so far in terms of finding the weight or finding the two components? All right. If we then just redraw those two components as if they were actual forces and then put them into the free body diagram, because even though they're not technically forces themselves, they're just components of a single force, we can always represent a single angled force as its components. So this isn't a normal free body diagram. This is an adjusted or edited free body diagram that illustrates the components. And you notice they've taken the red one off of the diagram entirely, because we shouldn't represent it both ways. We should either represent it as the force that it is, which was that angled red vector, or as the components that we can break it down into mathematically. And so here we're just doing a mathematical analysis and we just draw the components only. So how would I find that normal force now based on what we've discussed before? I know the vertical component now is 15 newtons. How do I find that normal force?
Would you just do the gravity minus the vertical component?
Yeah. If we think about the fact that the two upward forces of the normal plus 15 have to equal the weight force downward, the two up have to be balanced by the downward. So to find that normal force, we would take 50 minus 15 and get 35 newtons would be the normal force. I wanted to talk that through because I think that's the more direct mental approach, recognizing the free body diagram, recognizing the force balance equations, and knowing those two upward forces have to equal the magnitude of that single downward force. So it's a pretty simple problem if we approach it that way. I wanted to talk about that first because your book approaches it a little different, and I appreciate what they're doing in this approach. They're saying, hey, let's just focus on the vertical, which is what we did. But then they're saying, let's approach it just like we did all those systems problems before. They're trying to stay consistent with their approach. And I think there's some value to that, but I don't think this is naturally intuitive for most students, but I would like you to see it. So they're saying if we just focus on the y-axis, just the vertical, there is no acceleration. We wouldn't expect this box to rise up or fall down. It would just slide across the table. And so that acceleration vertically should be 0. So they're using more of the Newton's second law system of equations where we can say, well, in one way, the vertical forces, the net vertical force would just be the sum of all those vertical parts, those vertical components. So the normal force plus the 15 up plus the negative 50 since it's downward. But you can also calculate the normal force just by taking mass times acceleration. And we know the mass is 5, and we know the acceleration, vertically speaking, is 0. So they've just taken a more consistent approach with what they did in the previous kind of problems. And they still get the same answer. I think it's, like I said, less intuitive, but I wanted you to see it because it has some value perhaps in just reminding you that we can always take that Newton's second law system approach. Any questions about how to find that 35 newtons? Either way, the way Kayla suggested, which is also the way I would probably do it, or this way? All right, how about the acceleration? How are we going to find the acceleration? Let me go back a slide here.
Take the horizontal component, and since it's F equals ma, divide by the force by the acceleration, or divide the force by the mass, and get the acceleration.
Yeah, good. If we look at this version of the free body diagram where we've taken out the actual red force vector and just replaced it by its components, we know vertically they all cancel. That's the whole logic of the fact that they cancel is how we knew to find the normal. So vertically speaking, they all cancel out. They do not give a net force, but there's only one horizontal. Since it said we're ignoring friction, just that single horizontal component of the pulling force is the net force. And so, yeah, just like Ethan said, we can just, again, go to Newton's second law, and the net force would literally be that second, or that horizontal component of the red force we saw originally. And the mass is 5 kilograms, which was given. So we just divide to find the acceleration. This object would accelerate along the table at 5.2 meters per second squared. So if we see it in action, I think they have a little animation here to help you sort of visualize that happening. Any questions about that part, finding the acceleration, the second half of this problem? And for that one, I don't think there's really a lot of other approaches. That is about the only approach I can think of to figure out what that acceleration would be. All right, I'm not hearing any questions. At any time, if we're going through anything, if you need more time on a slide or if there's something that you want to ask, don't hesitate to interrupt me. I would rather you interrupt me so I know you have a question than you try to be polite and wait till I'm done speaking and then you forget what you're going to ask. Or we've gone on so far that it doesn't make sense anymore. So interrupt me at any point if there's something you want to ask. I will not be offended. All right, now these last two slides, I just want to give you a quick summary. And this, if you've been following along in your textbook, these PowerPoint notes really do flow pretty nicely with your textbook. And this is actually part of the summary at the end of the chapter 4. So you could just look in your textbook to see this, but I wanted to show it to you just as a real quick review. I do want to make sure you know the 3 Newton's laws. You are expected to know what they mean. You are not expected to quote them word for word from the textbook's version of the definitions, okay? You do need to be able to state them or understand them, and you also need to know which is which. So unlike the kinematics equations, which aren't technically numbered, we often refer to them by number based on how we learned them, but they aren't technically numbered. Newton's laws are technically numbered. The first one is the law of inertia, if you wanted to give it a short title. The second one is basically the equation we use, and the third one is that equal opposite idea. So you do need to know which law is which, because they might ask a question like, how does Newton's first law explain this? Or how does Newton's third law explain this? And if you don't know which one's which, you're going to have a difficult time making sure you apply the right narrative to your answer. So the first law is that law of inertia, that if an object's at rest, it's going to remain at rest. And if an object's moving, it's going to continue to move in the same direction and at the same speed, unless you apply a net force or unless you apply an unbalanced force to it. So just a restatement of Newton's first law. And then Newton's second law can be stated in words where we talk about the proportionality of mass and force to the acceleration of the object, that the force is directly proportional to the acceleration, and that the mass is inversely proportional to the acceleration. Or you can just write an equation if you're going to be trying to solve a problem. But that's what Newton's second law helps us understand, is the proportional connection of force and mass to the acceleration an object experiences. And then the third law is that whole equal and opposite kind of force pairs connection, that if an object A exerts a force on object B will exert a force on object A that is both equal in magnitude and opposite in direction. So nice summary. If you want to take a quick screenshot, you can. If you just want to look in your textbook, I think this is almost exactly pictured in your textbook. If you have it all in your notes already, you may not need either one of those, or if you just know them already, you may not need either one of those. But that is Newton's 3 laws summarized briefly. A couple other things from chapter 4 that they summarize, probably in some ways a little less important. I wouldn't necessarily have even thought for some of these to be put on a summary slide, but they are things you should know. One is that whenever we talk about mass, its unit is kilograms. And so they do want to make sure you understand the difference between weight and mass. Mass is measured in kilograms, and it's the description of how much matter is present in an object. Weight is a force, and force is represented in newtons. So mass and weight are different because mass is a property of matter. Weight is how much gravity impacts the mass, and it's measured in newtons. And so to calculate the weight, we would have to consider the acceleration due to the gravitational force field of the Earth. And therefore, we would take the mass of the object in kilograms times the 9.8 meters per second squared, which is the acceleration due to gravity. Or on the AP exam, you can use 9.8 or 10. On positive physics, 9.81. The normal force is another thing that I do think I would probably, weight and normal, I probably would have thought to put in my summary as well. I don't know that I would have thought to put necessarily those units, but it's good to review. The normal force, though, is the supporting force of a solid surface underneath an object. And it could be a table or a floor or the chair or the ground, but it's going to be that perpendicular force perpendicular to the surface. So if it's an angled surface, if it's the road and the road is sloped, then the normal force is always perpendicular to whatever that surface is. Or as we do in physics, we often put things on ramps. I'm not sure why ramps are so popular in physics, but you see all kinds of problems with objects on ramps. And so it's always going to be perpendicular to that surface. So remembering what normal force is. And then another force that we've talked about a bit here is tension force. So if there's a rope or cable or chain or something, then there's going to be tension in that rope based on the two objects that are connected, the rope and whatever the other object is. And I would say, they haven't put it here on this slide, but I would say something that often I've found helps students get uncaught or unstuck if they're caught on a problem that says something about tension is the simple phrase, ropes can't push. If you remember that ropes and chains and things that have tension can only pull on an object, sometimes that little phrase, for whatever reason, will get students unstuck when they're trying to get through a problem and they just can't get going. I don't know exactly why, but I've said it multiple times, and I've seen it even where a student just is trying to think about a pull in the wrong direction, or sorry, a tension in the wrong direction. So tension, ropes always pull, they never push. And if you think about it in real life, you can't use a rope to push on something. You can use a rope to pull on something. So just that quick reminder. So there is your summary of chapter 4. I would like to go ahead and switch to chapter 5. And continue on with some more examples. So I, again, would recommend read chapter 4 in your textbook, read chapter 5 in your textbook, go through the example problems that they work through. Some of them are what you see in these notes. Some of them are a little bit different. Definitely worth your time. You can see the big topics in chapter 5 are static friction, kinetic friction, and drag force. We've already spent a fair bit of time on static friction and kinetic friction last time, and we're going to spend the rest of our time today again, talking about those same two forces, but applying it in different kinds of problems. And so again, confirmation, we're not really learning anything new. We're just applying these things we've already learned in different ways. Drag force, if we have time on Wednesday, we may come back and review that a bit. It's more that you understand that it's basically air resistance or resistance of a fluid like water as something passes through, and that technically it could be considered a very unique style of friction. But when we talk about friction in this AP course, we're specifically talking about solid to solid contact. So they're separating it out, but it's still including it in the application chapter. So let's quickly review the difference between static friction and kinetic friction force. If you push or pull on an object to make it slide, but it does not move, we call the force presenting the sliding static friction. And we abbreviate it typically F with a subscript S. So if I have this object and I pull with 3 newtons, but it doesn't move, then the friction force must be 3 newtons resisting that movement, resisting that pull. If I pull with 4 newtons and it still doesn't move, then the friction force has to be 4 newtons because it's going to equal the amount of my pull to keep it from moving. If I pull with 5 newtons, the friction force has to be 5 newtons to keep it from moving. If I pull it with 7 newtons, the friction force has to be 7 newtons to keep it from moving. So it's like the normal force in that if it's able to keep it from moving, it will exactly match the force trying to make it move. Just like the normal force, if it's able to support the weight of the object, it will provide the exact amount necessary to support that weight. But if you put too much weight on the table, for instance, it will break. If you put too much force on the object you're trying to slide, the static force eventually will break. It can't hold it anymore. And so then the object will start to move. So that's why we saw last time, in some books, some curriculum, you'll see the friction force is less than or equal to, reminding you that it will just match whatever your pulling force is until it can no longer do that. If you remember the graph we looked at last time, that angled force of static friction compared to applied force, it just kept rising and rising and rising and matching the applied force until it reached the breaking point, and that static friction was past its maximum. And so at that point, it became kinetic friction and started to slide. which is the second half of this slide. If the object is moving, then we say that the force opposing that motion, not stopping the motion, but making it harder, is called the kinetic friction force. And we abbreviate it F with a subscript K. In this case, it has to be in movement. It might be slowing the movement down if there's no longer a force being applied. It just might be making it come to a stop. Or if we're continuing to apply a force, it may just be that force that's making it harder on us, making us work harder to get it to continue to slide. So any questions about the difference between static or kinetic friction forces? All right, the equation that we learned last time, you can see for static friction force, when we don't have motion, when we have it sitting still, that's the word static means, it's sitting still. It can have any value up to its maximum. So you can see they've approached it slightly different here in the textbook as opposed to the curriculum from New Jersey we looked at last week. The static friction force is, in this case, written as a maximum, and they've just used an equal sign. So instead of saying it's any amount less than or equal to that maximum, they're just saying, if you just calculate coefficient of friction times the normal force, that tells you the maximum that you would have to overcome to make it slide. And that little mu shape, funny U, is the coefficient of friction, and the little S beside it means you would need to look up the coefficient of static friction. So you would look on a table in your textbook, or they would give it to you in the problem, or they might ask you to calculate it, but it's not something you need to memorize. And then the normal force is thinking about the surface that the object is on. And it's always going to be perpendicular to the surface. So if it's a flat surface, it will be the same as the weight, because the weight will be straight down and the normal force will be straight up. If it's an angled surface, then you're going to have to do some trig to figure out how much of the normal force is compared to the weight. They won't be equal if it's at an angle. The normal force will be a different value. You'll have to find the y component of the normal force to figure out how it compares to the weight. So any questions about the equation? All right, let's think about one other topic. I think maybe in this class, I think it was this class, someone asked about surface area. And this is where we highlight the fact that in AP Physics, we're limiting our discussion of friction to solid-solid contact. So when we're talking about solids in contact with one another, the surface area doesn't impact the friction. And if we think about, I like the picture here because they're showing different shapes that have different amounts of surface area, but they're also showing that all of these shapes have the same mass, and therefore they would all have the same weight. And since this surface is flat, they would also have all the same normal force. So that first little square on the left has a normal force of 30 newtons. The table would provide a normal force of 30 newtons. And the weight would be 30 newtons down. But that weight is distributed over a certain amount of surface. And so it's the pressure that's different, not the friction force. If I compared that to the next rectangle, it has more surface area, but it still has the same mass. So the weight is just distributed over a larger area, which changes the pressure, but it doesn't change the friction force. If we have a rectangle oriented the other way with the smaller side, that would create a lot more pressure. So for instance, if you, for any of you that have ever worn high heels, I actually haven't, but if you've worn high heels, you've maybe noticed that like walking across ground, if it's soft ground, your heels can dig in. It's not the toe part that digs in, it's the pointy heel part, right? And so it's because there's more pressure on that skinny part than there is on the broader toe part. And so if you have a small surface area, that increases the pressure, but it doesn't increase the friction. Now, if you were changing the surface area and at the same time changing the mass, that's a different scenario, because when the mass changes, then the normal force changes. But it's the normal force that controls friction, not the surface area. The surface area just changes how much pressure there is on that surface. It's either spreading it out over a larger area or limiting that pressure to a small area, but that won't control the friction. The normal force is still the same. All right, let's look at the coefficient of frictions again, just as a quick reminder. You have to look this up or be told these values, or they might ask you, they give you other information and ask you to actually calculate it, but it's not something you need to memorize. And again, just a quick reminder, as you look at these highlighted static coefficients, they are in all cases either bigger than or equal to the coefficient of frictions for kinetic motion. And so if you look at the categories, there's only one where it's actually equal. Teflon on Teflon, both are about the same, whether it's moving or whether it's not. And for those that have had chemistry, Teflon is a highly non-polar substance, which means it creates very little intermolecular forces. And since there aren't much intermolecular forces, there's not really much difference between whether it's moving or not. At least that's part of the reason. But for most things, there is a bigger difference. Yeah.
Is there any material where the sliding is greater than the static, or is it for all materials?
I have not heard of any where it's greater. I suppose there may be some, like if you've ever heard of oobleck, there's some like non-Newtonian fluids that have unique characteristics. I suppose there may be some strange material that's been created that has that. I have not heard of any though. And I actually researched it once, but it was several years ago. At that point, there wasn't anything that I found in my research that had a larger sliding friction coefficient than static, but there are a number that are equal.
Cool.
Yeah. All right. So let's practice a couple problems here. In this first problem, it says calculate the static maximum friction force. What is the maximum force of static friction for this block? We've got a 4 kilogram block of steel on a copper tabletop. So what do we need to do to find the static friction force? What are we going to put in our equation? What are we going to need to, steps we're going to take? What do you think? You don't have to tell me the whole problem, just what's something we have to do to solve this?
We need the coefficient of friction for the copper.
Okay, there you go. I just looked it up for you.
Thanks.
What else do we need?
Our equation of Fs max equals the coefficient of friction times the normal force. Oh, so we're going to need the normal force.
Mm-hmm. How are we going to find the normal force?
The mass of the steel times the acceleration due to gravity will give us the force due to gravity, and then we'll just reverse the sign for the normal force.
All right. Yeah, it's a flat surface, so the weight and the normal force will be equal in magnitude and opposite in direction. I'm going to put you in breakout rooms and give you about 3 minutes to go through those steps, maybe discuss it. If you have questions, if you're not quite following the discussion here, you can talk about it in a smaller group and make sure you understand it, and find the answer for this one. You know the coefficient of friction is 0.53 for copper and steel at static status. And you know it's a 4 kilogram block. So using what we've discussed and what we've learned, find that friction force in your groups. Like I said, about 3 minutes, and then I'll bring you back and we'll see what you came up with. I believe we have everybody back in the main room now. So Rocky, what did your group come up with for the answer to this one?
20.7972.
Okay. Did you use, what did you use for your value of G?
I used 9.81.
Okay. So getting in practice for that positive physics where they require that. So the steps, find the weight of the block. So we take 4 times acceleration due to gravity. They used 10 here in the textbook. So you got 39 something probably here for this weight force. And then we know that, like Ethan told us before the breakout room, the weight and the normal force must be equal and opposite since it's a flat surface. So we can think through that the normal force and the weight force have to balance out to 0 net newtons. And so if the weight is -40, the normal must be +40. And if we know that the normal force is +40 and the coefficient of friction is 0.53, we get 21 newtons. So if you use the 9.81 or 9.8, you get a slightly different value for a couple of these steps. But if we look at the sig figs, the coefficient of friction is 2, and the 4.0 kilograms is also 2. So if we were following the sig fig rules strictly, it would be 21 newtons. Now, remember, on the Positive Physics website, in the bottom corner, it gives you that reminder, use 9.81 and give all your answers to 3 sig figs or more. So, or I think it says to at least 3 sig figs. I think that's how it phrases it. So even though it may, like in this question, the answer technically is 21, you should give it, if you used, well, you should use 9.8. So what did you say it was, Rocky, with when you did it?
20.79.
Yeah, so you would do 20.79 or 20.8. You'd have to have at least 3 sig figs. And it does have a variability in the way it grades it. So I forget what the percentage is, but it automatically calculates a flux in either direction in case you round a little bit differently, or if you round differently at different steps. Some students might calculate this on their calculator all in one step where they never actually round until the final answer. Some might round it when they calculate the weight and then round it again on the final answer. So that gives slightly different final results. So there is some flexibility in that. All right, questions about that example? All right, let's keep moving then. In this scenario, we have at the top a reminder that the coefficient, or the maximum, not the coefficient, but the maximum static friction is 21 newtons. And in this case, they're saying, okay, if the pull was 15 newtons, and that means the static friction would be 15 newtons in the other direction, the steel doesn't move, the velocity is 0, there's no acceleration because there's no net force. We haven't reached the maximum capacity of the friction between these two surfaces. So pulling it with 15 newtons won't move it. Pulling it with 20 newtons, it's getting close, but it still won't move it. This object won't move until we surpass that 21 Newton value. Okay, so even if it really is exactly 21, even if we went to 20.9, it wouldn't move until we reach that maximum. So since we're saying it's 21 and this, the way they've calculated it, we're saying that it would not move until we surpass that 21 Newton max. So if we did pull with 25, that is beyond the 21. And so that static friction could no longer stop it from moving. And then it would just be the kinetic friction. So you can see they've changed the words here. Kinetic friction is what would be in play now. And so it would be moving. And in fact, since that's so much greater, the 25 than the 21, it would be accelerating. All right, any questions about that concept? Just recognizing when it would start to move and why?
If it was exactly 21 and you pulled with exactly 21, it wouldn't move, right?
Right, it would have to slightly surpass it. Mm-hmm. Good. Now, keep in mind, if you remember that graph, it went up, 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 and then when it reached the max, it actually dropped because for almost all substances, the coefficient of kinetic friction is less. So once you break the static friction and it starts to move, then it's actually going to require even less force to keep it moving. So it will definitely be accelerating in this scenario since it's 4 newtons greater than the static friction. That's going to be even more than 4 newtons greater than the kinetic friction that's required to keep it in motion. Thinking of kinetic friction then, here's quickly the slide that reminds us the equation is basically the same. The only thing you need to change is instead of looking up the coefficient of static friction, you need to look up the coefficient of kinetic friction. Everything else is the same. It's still going to give us the friction force. It's still going to require knowing the normal force or finding the normal force. But you would never see this one as a less than or equal to. It's always just equal to, because it has to be in motion for us to be considering this. And it doesn't matter the surface area, as we learned before. It also doesn't matter the speed. So if you look at the equation, it's only the coefficient. So what are those two substances? That's what the coefficient tells us. How slippery are they? And the normal force. It doesn't factor anything else in. So as we said before with static, surface area doesn't matter. That would just change the pressure, not the normal force. And the speed that it's moving also does not matter. Now, there are some limitations to that speed. If the surface is rough enough and you're pulling it at a big enough speed where it would start to bounce around and lose contact, that's a very complicated scenario to try to think through. So we're assuming, again, in our AP physics level, that one, we're only dealing with solid to solid contact. We're not dealing with air resistance or water drag or something like that. And we're also assuming it stays in contact the whole time. All right, so we're kind of taking some assumptions and making it an abstracted, very sort of basic level scenario, which gives us a good approximation for most systems. All right, so reminder, as we said before, if you look again at the list, the static friction coefficients are almost always larger. Occasionally you'll find some that are equal, but typically the static friction is going to be larger. So normally once it starts moving, it will be easier to keep it moving than it was to actually get it started. And again, you never need to look these up. And in fact, if you compare if you Google it, like coefficient of friction, and you Google it, some of these numbers might be different on different websites. So there's no reason to copy this list down. They're going to give you a list to use, or they're just going to give you the number. Okay, you're never going to have to know it. And there is no one list that all scientists agree upon. In fact, these numbers are constantly changing because they're experimentally derived. And steel on steel, technically there's multiple kinds of steel. Okay, so because steel is an alloy, so we won't get into that. That's a whole chemistry topic. But so these are just to give you an idea of how they relate. All right, so now let's talk about a friction force when things are moving. You can see now it's saying calculate the K friction force, kinetic friction force for the steel on copper steel still. So it's a 4 kilogram block of steel on a copper table, but now it's moving. It's not sitting still. And then here they've given you the coefficient of friction again, the 0.36. So let's have you go back into the breakout rooms, figure out what is the coefficient, or not the coefficient, what is the kinetic friction force based on this 4 kilogram block of steel and the coefficient of 0.36. All right, give you about 3 minutes to figure out what the value of the kinetic friction force is. All right, I think we're all back in the main room now. Kyle, what did your group come up with for the answer to this one?
Oh, we got 14.1264 or 14.1.
All right. So I'm sure you did pretty much the same as before in terms of finding the weight. Did you guys use 9.8?
We used 9.81.
9.81, okay, good. So you get a slightly different value there. And then recognizing it's a flat surface, so that normal force is the same in terms of magnitude as the weight force. And then plugging in, we take our coefficient of friction, which is different. It's less because it's already moving now. And so while it took 21 newtons of force to get the steel block moving, it only takes 14 newtons of force to keep it moving. And so that's the difference between coefficient of static friction and coefficient of kinetic friction. We see how it impacts the overall force required to start an object's motion and to keep it in motion. All right. So if we think about this, we've basically changed this problem into this free body diagram, right? We've got our 40 Newton weight force down, our 40 Newton force upward for normal force, and we've got our 14 Newton force backward. And what we're saying here is this object was given a good shove, and now it's just been sliding along the table. This metal is just sliding along, the steel sliding along the copper. It's no longer being pushed, it's just sliding. If it was being pushed, that'd be a little bit different scenario, but here it's just sliding. You can see they're not showing a forward force. It's only the backward force of friction. So since there's no forward force, it's just only sliding at this point, going to probably eventually come to a stop, we would assume, with that forward velocity. So the next thing they want us to do, though, with this information is determine, okay, well, now that we know all this and we've sort of drawn a free body diagram to represent it, what's the acceleration of this block? So before we calculate it, what would the sign of the acceleration need to be? Is it going to be a positive value or a negative value given these circumstances?
The acceleration is going to be negative.
Okay, and how do you draw that conclusion, Ethan?
The force is to the left, and so the acceleration will, if the force is negative and the mass is positive, then the acceleration is going to have to be negative.
Good. And so we could focus on the force of it itself. The net force is in the negative direction. And if you recall from our notes a couple sessions ago, I think it said 8 or 10 times, the direction of the net force and the direction of the acceleration are always the same. So if this net force is in the negative direction, then the acceleration also has to be negative. There's another way you could also think it through, thinking back to kinematics. What's the sign of the velocity? Based on what they've shown on the screen here, what's the sign of the velocity?
At the beginning, it's going to be positive, but then as soon as the acceleration's large, or I guess as soon as it accelerates for a long enough time, it'll become negative.
So would friction ever cause the object to move backward? So right now it's got a
Oh.
Go ahead.
Yeah, no. Oh, be positive until it stopped.
Yeah. So it's going to be positive until it stops. When it stops, how does this free body diagram change?
Wouldn't it be the static friction instead of the kinetic if it's not moving?
Yeah, the kinetic friction no longer applies because it's not moving. Would we put static friction on there if it just stopped?
No, because there's no velocity.
Yeah,
there's no force acting on it.
Yeah.
So the static friction wouldn't have anything to balance.
Good. Yeah. So once it stops, it can't be kinetic friction anymore because kinetic literally means motion. There has to be velocity. So once it stops, the kinetic friction ceases to be a factor. And unless there's some force pulling it, static friction also doesn't matter. If there's no force pulling it, static friction is 0. So if it's 0, we don't draw it. So at the point when it stops, it's just the normal force and the weight, unless there's some other force pulling it or pushing it. Okay, just want you to think through that. So back to my question, Ethan explained it from the force perspective, but from the kinematics perspective, if the velocity is positive and it's slowing down, if it's slowing down, the velocity and the acceleration have to have opposite signs. Okay, that's our kinematics rule. If an object is slowing down, the velocity and acceleration have to have opposite signs. So since it has a positive velocity, if it's slowing down, the acceleration has to be negative. So you could think about it from a kinematics approach or a forces approach. Either way, we know the acceleration has to be negative. How are we going to calculate it? What are we going to use to calculate the acceleration?
Newton's second law.
Newton's second law. Good. So Newton's second law tells us the sum of the forces is going to be mass times acceleration. Well, there's 3 forces here. What's the net force?
$14.
Why don't we have to think about the 40s?
They balance each other out.
Yeah, they cancel each other. So the only force that doesn't get canceled out is the 14. And like Ethan said, it's backwards. So the force is in the negative direction. So we plug that negative 14 in for the force. And we were told in the beginning, the mass of the object was 4 kilograms. So to find the acceleration, we just divide. And the acceleration should be negative 3.5. Like we said, it should be negative because it's slowing down and it has a positive velocity. Or because the net force is in the negative direction, therefore the acceleration also must be in that same direction. Questions? All right, so we've revisited static friction, we've revisited kinetic friction. We've talked about a couple of different examples for each. And we started the class with an angled force where we had something pulling at a 30-degree angle. That's all I wanted to get through today, just practicing those kinds of problems. On Wednesday, we'll take what if there's both friction and an angle, and we'll go through some problems like that. All right. For today, though, that's all I have. Just wanted to practice a bunch of different problems with you. And for the last 20-ish minutes, if you have questions for me about studying for the review, or sorry, studying for the exam, or working on positive physics, you're welcome to stick around and ask those questions. But if you don't have any questions, you may be dismissed at this point, and I'll see you next time.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you,
You're
Mr.
welcome.
Webb.